Hey everyone, I'm Elif. This is the first lecture of the Introduction to Algebraic Function Fields and Codes. Before starting with the foundations of this theory, in this short video, I just want to give some information on the structure of the course, and we recall some background from field theory that we will need to use throughout the lecture. As you may know, this course is scheduled on Tuesday and Thursdays between 10:15 and 12. However, regarding the experiences we had in previous 2 semesters, we will prepare video records instead of having long Zoom live sessions. And you will receive them on the previous day of the lecture days. So that means on Wednesdays and on Mondays and Wednesdays. You will receive 4 links, and each link contains approximately 15 minutes video records. I want to remind you that you can watch these videos during the regular hours. However, whenever you watch, I want to kindly recommend you to follow these records by taking notes and understanding each step. To increase the interactive learning and to be able to discuss the parts you are not convinced in the video records, we will set up 30 minutes discussion sessions on Tuesday and Thursdays. And these discussion sessions will be held over Zoom, and you will receive the Zoom link in the announcement email. And in these sessions, I would like to encourage you to ask your questions. And I'm also planning to ask you provide some examples or the definitions that I covered in the related video records. And your attendance will be important to increase the interactive learning and discussing mathematics between us. So this is why I look forward to seeing you on Tuesday in the first discussion session after watching the videos. And as a supportive document, we will use Google Docs. And you can find its link in the announcement email as well. You can post your questions, comments, and suggestions on the course or the topics or the material that we covered. Okay, now let me recall some fundamental definition from field theory. In this course, our main object is a field, which is defined as an unempty set with 2 binary operations, addition and multiplication, and that contains their identities 0 and 1. And each element has an additive and multiplicative inverse in L. And a subset of a field, L, is called a subfield if it forms a field with respect to same binary operations. Or equivalently, we say that L is a field extension over K. And we will denote it by this notation or this field extension diagram. And whenever we have a field extension L over K, we can view this extension field as a vector space over the base field. And its vector space dimension defines as the extension degree of this extension. When we have a finite dimensional vector space, so that means whenever we have finite extension, we often consider a basis of L over K. And this allows us to represent every element in the extension field L, let's call it gamma, is a linear combination of these basis elements with the coefficients from the base field K. When we have chain of or towers of field extensions, by using the basis representation, we can see that the extension degree M over K is determined by the extension degree of each step that appears in the extension. So that means if it is finite, these should be finite, or vice versa. And an element in the extension field is called algebraic over K. If it is a root of non-trivial polynomial with coefficients the base field from K. So that means, that means there exists a non-trivial polynomial f of x such that alpha is a root of f And next week, in one of your homework question, you will see that there exists unique monic irreducible polynomial which contains this algebraic element as a root. And such a polynomial P of x is called the minimal polynomial of alpha. And when we have an algebraic element, we will define the simple extension or the intermediate field K and L, which is the smallest field. That contains K as a subfield and the algebraic element alpha. In this case, the extension degree of this simple extension is determined by the minimal polynomial of the algebraic element. And again, in the same case, we will also say that this is a degree of the algebraic element alpha. As a generalization of simple extension, we can also consider the smallest field that contains K as a subfield and the given n elements in L. And if every element in the extension field L is algebraic, we say that this extension is an algebraic extension. If every gamma in L is algebraic over K. And here, I forgot to point out that, okay, we have a finite dimensional vector space and we can explicitly consider a basis which is formed by the powers of this algebraic element alpha. And finally, we say that an element in L, the element X in L, is transcendental over K if it is not algebraic. So that means there is no polynomial in the polynomial ring K of X which contains this capital X as a root. As an example of a transcendental element, we may consider the variable X in the polynomial ring. And in this lecture, our main object, one of the important object, which is defined as a set that contains the fractions of polynomials from K of X with non-zero denominators. And this set is called a rational function field. And as a simple exercise, you may check that it forms a field. And this also can be seen as an extension over K, but since X is transcendental, this is not going to be finite extension. In the next video, we will continue our rational function field, and we will define what is an algebraic function field. And in the discussion session, probably I will ask you to provide some examples for fields, for simple extensions, algebraic extensions, etc. And please feel free to ask your questions about this video in the discussion sessions. See you in the next video, and bye-bye.